Hey there, I'm srcmake, and welcome to the video on the interview question about reversing an integer, which also happens to be this LeetCode easy problem. Now, even though this is an easy problem, there is a lot of foundational knowledge that we can gain from this problem, and it turns out I was asked a very similar problem in an interview with a finance company in New York, and it turns out even if you were to get like the 100% time solution on LeetCode, it's not necessarily what the interviewer wants to see. There are a few steps further that we need to take it to get to the real optimal solution. And so we're going to be looking at that and working toward that in this video, so please do try to stick around until the end. So in this video, we are going to look at the problem statement and a few examples. Then we are going to look at the string solution, just some real quick pseudocode without handling the overflow case, just so we understand like a basic solution to this problem. And then to actually look at the overflow and understand what's going on, we need to understand binary numbers and how an integer is represented as bits, and that's what we're going to be doing in this section. So we're going to go over bits in details in this section. And then with that knowledge, we're going to come back to our string solution, and we are going to handle that overflow using a 64-bit integer. Spoiler alert, 64-bit integers are not what the interviewer wants to see. That's not really acceptable in a real interview. But it is acceptable on LeetCode, so some people might solve this on LeetCode and think they got a real solution when really it's not good enough. So we're going to look at the string solution, talk about it. I've got some C++ code written out here that we're going to go through. It's very similar to the pseudocode, and you can see that these lines are really short and easy to understand. So if C++ isn't your favorite language, don't worry about it because it'll be understandable anyway. So we're going to go through that, and we're going to run it in LeetCode to make sure that it works. Turns out it is going to be a working solution, but we can do a little bit better. So we're going to work toward the mathematical solution, also using a 64-bit integer. You'll see that only a few lines of code change. This is C++ code as well, but only a few lines from the string solution change, but it turns out to be a much better solution. So we'll be going through that, but it's still not the optimal solution. The optimal solution would not be to use 64-bit integers, but to only use 32-bit integers. So we're going to upgrade our mathematical solution using only 32-bit integers. We'll see that a few lines of code change to make that work, but that will be what is really acceptable in a real interview. So we're going to be working toward this. Please try to stick around for this section and stick throughout all of it because we're going to be building our way up. So if you need to get to this webpage to see this code or get to the LeetCode page, there will be links below this video, and while you're down there, hit the subscribe button to this YouTube channel. Thanks. And I really do recommend bookmarking this page because this is a really good interview question that represents a broad category, and so if you understand this, you can understand a lot of things, and it would be good to brush up on this before real interviews. I know that's what I'm going to do. So the problem statement. Given a signed 32-bit integer, and we'll understand what this means in a bit, given that integer, reverse its digits. And if there is an overflow after the reversal, then return 0 instead. And we'll see what overflows mean in one of the future sections. So, for example, if we were given the number 123, we would reverse the digits and return 321. If the number was negative, then we would keep the negative sign and do the reversal on just the digits. So for example, if we were given negative 456, we would return negative 654. And then there's this weird case here that actually means nothing for our code, but I guess we need to keep it in mind, is if we were given some number that ended with a 0, we wouldn't want to have any leading zeros in our reverse number. So for example, 780 reversed is just 87. It's not like 087 or something weird like that. And finally, for a huge number, if we were to try to reverse it and it would overflow, like this number, for example, we would just return 0. So that's what the problem is asking us to do. It actually does sound easy, and this is an easy solution. It's the string solution. So working with integers and the digits of integers is not easy, but working with the characters inside of a string is easy. So the easy solution is to convert our integer to its string representation, reverse the characters in that string, and then convert that string back into an integer, and we can return that. So that's a really easy solution. In the case of a negative number, we just have to do something a little bit different. We want to make it positive for the string conversion, and then we can make it negative again before we return it for the final answer. So let's look at this pseudocode. I'll make this a little bigger so it's easy to see. We've got a function here named reverse. It's going to return that integer, and it's going to get passed in the integer that we want to reverse. First thing we do is check if the number is negative. We will store if it's negative or not in this boolean named isNegative. If the number is less than 0, then this will equal true because it will be negative. If the number is not less than 0, which means it's greater than or equal to 0, then the number is positive, and so isNegative will equal false. That's what this ternary means. Bool is negative. So if it is negative, then we want to convert it to positive so that we can work with it a bit easier. So we just multiply it by -1. Then we do the magic. So we get the string representation of the number. We put that into some string named s. We call some magic function named int to string on our number that converts the integer to a string, which is going to be s. Then we want to reverse the string, so we say s is equal to reverse. Some function named reverse is going to reverse s for us. And finally, we want to convert that string back to an integer since it'll be reversed. So we say the reverse number is some integer, and we get that by converting our string to int on s. And then finally, if the original number is negative, we want to make it a negative again. So we say if it was negative, multiply the reverse number by -1 so that it can become negative. And then whatever it was, we just return the reverse number. And so this is a really easy to understand pseudocode. But you'll find that it doesn't work on LeetCode because it's pseudocode first of all, but if you were to translate it to a real language, it doesn't handle the overflow case. So to understand overflows, we kind of have to understand how integers are represented. And basically, since we're working with 32-bit integers, that's what we're going to do in this section right here. A 32-bit integer is literally just 32 bits, a bit can be 0 or 1, that are put together in binary format. And so if we look at this example right here in the diagram, we've got 32 bits. They happen to be 32 ones. And the way you read a binary number is you go from right to left, and this first digit represents the zeros place. The second digit represents the ones place, and you keep going on like that. And so when you want to convert this binary number to its decimal value, decimal being base 10, which is what we're used to working with, you say if this value is a 1 at the zeros place, you add 2 to the 0 to our decimal value, to the value that we want to get. If this ones place is a 1, then you add 2 to the 1 to our final answer. If this 2's place is a 1, then you add 2 squared to that answer. And you keep going, and since we have 32 bits, we go all the way to 2 to the 31. And so if you were to add each one of these and do the, power operation up, then you would see that 32 bits, the maximum value you can get if they were all 1, would be 4.2 billion. Specifically, 4294967295, whatever that number is. That's if every single one of those 32 bits was a 1. That's the maximum number we can get. So for a unsigned 32-bit integer, the maximum value is 4.2 billion. And so the range of numbers that we can represent using these 32 bits would be from 0 to 4.2 billion. For it to be 0, all of these 32 bits would be 0, and then all of them, none of these would get added, and so we would just have 0. Or maybe some of them are 1s, but not all of them, and so that would represent some number in between, like, 5, 2 billion, 1 billion. One of those numbers would be in between if one of these was 0. But the maximum we can get is of all 32 of them are 1s, which is what that 4.2 billion is. So that's an unsigned integer, meaning we don't care about negatives, and that's why we can have an unsigned range from 0 to 4.2 billion. But a signed integer means we want to be able to include those negative numbers. And so the easiest way we can think about, how can we get this 32 bits to represent our negative and positive numbers is if we divide that 4.2 billion, that maximum value, in half, and we say half of that is going to represent the negative numbers and half of it's going to represent the positive numbers. And so if we were to divide the 4.2 billion in half, that's going to equal 2.1 billion. And so the range that we can represent for the signed integer, including the negative numbers, is going to be from negative 2.1 billion all the way up to 2.1 billion. And so that means any number in between negative 2.1 billion and 2.1 billion is representative in our signed integer. Could be negative 5, could be negative 1 billion, could be 5, could be 7. Anywhere in between is a valid integer for our 32-bit signed integer. And one thing to note that's really important is that these are not the same number. you can see that this one ends with an 8 and this one ends with a 7. And the reason is because this 4.2 billion, the one that we got for the maximum value, can't be divided evenly. And so there's going to be one that's left over, and so we just shift it over to the negative side so that the negative gets one more value able to be represented. That actually came up in my interview, so try to understand it because that's really important, or it might come up in the future. So takeaway message is bits are, we've got this integer that's represented by 32 bits. For a signed 32-bit integer, the range is going to be from negative 2.1 billion to 2.1 billion with these numbers specifically. Those are that's the range. The lowest number we can get to is negative 2.1 billion. The highest number we can get to is 2.1 billion. So with that knowledge in mind, what overflowing means is if we go over that value or under that value, or which basically means outside of that range. So looking back at the problem of reversing a signed 32-bit integer. Sorry, I need to change this. But reversing a signed 32-bit integer means if we were to try to reverse, for example, 2.1 billion with this, then we would get like 7.4 billion. But this is obviously outside of the range of a 32-bit integer. So we're not allowed to, do that. That would be an overflow because that's over the maximum value that the signed integer can be. And so the problem would ask us to return 0 in that case. So one easy way to handle these overflows is to use an even bigger integer. We can use a 64-bit signed integer to store the reverse value. And so the range for a 64-bit integer, it's the same calculations before, but it's like this huge number would be the negative, and you can go in between this value and like this value. And I don't even know how high this is. This is obviously higher than like 7.2 billion. So a 64-bit integer will comfortably be able to fit any reversed 32-bit integer. So if we use a 64-bit integer, we can solve this problem very easily. So the difference in our code, now we have working C++ code. Let's go through it. Still a function named integer that passes in some integer named x. What we want to do is we want to convert x to a 64-bit integer, which in C++ is a long. That's the name of the type. So our number is going to be a 64-bit integer. Check if it's positive or negative. Convert it to negative if it convert it to positive if it was negative. Then we want to convert the number to its string representation. We want to reverse the string. This is just C++ syntax, but it's the same as the pseudocode. We want to convert the string back into the long, or the 64-bit integer, with string to long, that function. And if the original number was negative, then we want to make our reverse number negative again. So we just do this multiply by -1. But here's where we handle the overflow. So the minimum value that we can have for a 32-bit signed integer is the negative 2.1 billion. The maximum value, the top value we can have, is 2.1 billion. So we've just got these two if statements. If our number was originally negative, and if it is below the minimum value, which means it could be like -7 billion or something like that, then it overflowed, so we have to return 0. If the number is not negative, which means if it was positive and the reverse number is greater than 2.1 billion, then we have to return 0 because we overflowed. If it was like 5 billion, then we overflowed. The maximum we can store is 2.1 billion, so return 0 in that case. And the reason we have to have two separate if statements is because these are not equal values, right? These numbers are very different. One ends in 7, one ends in 8. And it's sort of like this weird edge case we need to keep in mind. So let's run this in LeetCode really quickly to make sure that it works. Oh, come on. Let's just run it because I want to show you that it's not like the optimal solution. We can actually, it's not going to be 100% time complexity. So I hit run code to make sure that it compiles. Come on, you can do it, LeetCode. It accepted. I hit submit code. Sorry, it was like right here. And you'll see 4 milliseconds, 48% time, not the best solution. How can we do better? Well, we can use math. So it turns out our solution is order number of digits. We have to go through each digit in the number, but these are expensive operations. So we have to convert the integer to a string. We have to reverse the string, and then we have to convert it back to a number. Those are expensive computations to perform. So if we were to do some mathematical solution, it would be better. And basically what we want to do is we want to go through each digit of the number from right to left, and we want to make that digit, we want to put that in our reverse number. So let's see how that works. So some more C++ code. This code is exactly the same. Check if negative, convert it to a 64-bit integer, multiply to make it positive in case it was already negative. And then this right here is the same. Convert it back to negative if necessary, and then check if it overflowed. The only difference is from where we used to do convert to string, then reverse the string, then convert back to an integer. We're not doing that anymore. We're doing this thing right here, few lines of code difference. Basically, we want to go through each digit and the number. And so our reverse number is going to start out being a 64-bit integer that is equal to 0. And we're going to process the number until we chop it away until it becomes 0. But basically, we want to go through each digit. So the first digit that we go through is going to be on the right, and we can get that by doing a modulus 10. So I'm going to open this up in Microsoft Paint really quickly. If the number is equal to 1, 2, 3, then 1, 2, 3 modulus 10 is basically the leftover. The modulus operator is the leftover if you were to divide by 10. In that case, is 3. And so the digit that we're going to be working with is 3. So we get that digit, we divide by 10. So 1, 2, 3 divided by 10. Sorry, there should have been a 10 here. 1, 2, 3 divided by 10. In computer science, or at least in C++, anytime you do division, it always rounds down. So this is going to be 12. So we get the digit, which is going to be equal to 3. We make the number 12, and then we say the reverse number is equal to reverse number times 10. We basically shift everything over, and we add the digit. So reverse number, which I'm just going to say is r, is going to be 0 times 10 is 0 plus 3 is 3. Let's just do one more iteration of this while loop to make sure we understand. So number is equal to 12 right now. If we do the modulus, the digit is going to be 2. We're going to say the digit is equal to 2. We divide by 10, so this is going to turn into a 1. And then we say reverse number is equal to whatever it is times 10, which is going to be 30, plus the digit, plus 2. So it's going to be 32. And we kind of keep going with that. So the takeaway message here is now we're using math. We are getting each digit individually by using the modulus 10 arithmetic. Then we get rid of that from the actual number by dividing by 10 and rounding down. It's going to round down. And then we just add that to our reverse by multiplying whatever it is by 10 so it shifts over, and then adding that new digit to the reverse value. And so that's the math way, really simply. It's actually, my programming master actually showed me this in college a long time ago, 6 years ago, and it seemed like so magical to me. I took it for granted, but that's a really powerful trick. So this code works. I'm going to submit it, and you'll see it should be 0 milliseconds, 100% time. So most people would stop here and think they're good to go. But that is a trap. An interviewer is not going to want you to use a 64-bit integer. So this is the final section right here, using only 32-bit integers. In a real interview, if you're asked this, you're not going to be allowed to use a 64-bit integer because that's basically like cheating. You're basically like throwing more hardware, or in this case bits, at the problem. And we want to be able to stay in the confines of the types that we have. And this is true for like low-level programming, right? Or if they ask you to reverse a 64-bit integer, are you going to have to like find some 128-bit library to let you do the reversal? No, of course not. You have to work within the types you're given. And so since we're given an integer and we're supposed to return an integer, we should stick within integers. And so let's look at the code. Basically what we're going to do is, instead of handling the overflow at the end, we want to, at each step of our math, check if we're going to overflow if we were to add that new digit. So we're just doing the check for overflow at each step instead of doing it at the end. So let's look at our code. This time we are going to check if the number is negative. We're not going to multiply it by negative this time because we're only working with these integers. So you might ask why. This is actually not that intuitive. But if you go back here, you'll see that this is a maximum. Actually, let's go back over here because it's a lot easier to see. This is the maximum value that you can go to the minimum value, and this is the maximum value that you can go to. And so what happens if they pass in this number and they want to try to reverse this number? Well, if we were to multiply it by -1, we would overflow because we would go over this value right here, so we can't even multiply it by -1 because that's an overflow, so that's not allowed. So we're not allowed to multiply it by -1 anymore, which is really fun to think about. So we can't multiply it by -1. Doesn't change that much, just we're going to have to do something different over here. And the other thing that changed is we're still going to multiply, make it negative if necessary at the bottom, but we're not handling the overflow last. We are going to be handling the overflow right inside of this while loop. So same code basically as last time. Start out with reverse number 0. Try to process each digit inside of the number one by one. So calculate the digit and then remove it from the number that we're working with. This time, if the number is originally negative, then it's going to turn out to be negative. So that means, like, if you were to be given -123, when you do this calculation, the digit is going to be -3 for the first value instead of +3, since we never multiplied it by negative. So if the original number is negative, then we just want to convert this, what would be like -3 to a +3 so that we can add it properly. That's just what this if statement does. Then here's where we and also right here, this line of code is the exact same. Just shift everything in the reverse number over and then add that new digit that we just added if everything works out. But we handle the overflow right here. So if this particular iteration would make us overflow, then we would stop and return 0. We have to handle the overflow right here, right now, before doing any addition to our reverse number. So if the reverse number is greater than this value right here, then return 0. What is this value? This value is our 2.1 billion value, the first like few digits, except for that last one. So basically the way to think about this is if we were to go to like 3 billion or something, like let's say we were at like, I don't know, 300 million. Let's say we were 300 million and we were about to add a new number. That would raise us up to 3 billion, which would be an overflow. So that would not be allowed, obviously, because we're adding a digit to something that's over the 2.1 value, so return 0 in that case. The other interesting case is if we're like really close to the edge. So if we were like exactly at this value, but we're about to go over that 7 for the positive case, or we're about to go over that 8 for the negative case, we're not allowed to do that. We're just like one value over. So we would return 0 in that case, where we might like right be at the 2.1 billion mark, but we were about to go 1 over instead of being under, so we would return 0 in that case. And so you can see the difference now is we're only working with 32-bit integers. There's no more long in this code, which represents 64-bit integer in C++. You can see the reverse number is just int, which is really good. We're staying within the confines, and so this is actually a solution to the challenging problem. So let's copy this and make sure that it works. The question is it going to be as performant as a mathematical solution? I think the answer, it might be yes on LeetCode, but the answer really should be no. So we'll see what happens. LeetCode's probably, so the answer is no. The reason is because now at every single digit, we're doing even more operations. You can see back over here, we only did these three things inside of our while loop, and then we handled the overflow exactly once. Over here, we have to do this overflow every single time we process a digit. And in the case of negative numbers, we also have to multiply by -1 every single time instead of doing it that one time at the beginning. But this is the optimal solution. So just to recap, the optimal solution is to use math, and we do a modulus to get that final digit, and then we want to shift everything over for our number by dividing by 10. And then we add that to our reverse digit in a certain order. But the way we can stick with 32-bit integers and not 64-bit integers is by doing the check inside of our while loop every time we try to process a digit instead of doing it at the end. So if we're about to overflow, return 0. That's when we have to do the check, not at the end when it already overflowed. It's too late at that point to do the overflow. You have to do it before it happens, which is what the optimal solution is. So that's basically the reverse integer problem. Hopefully I went over binary numbers well enough and you kind of understand what's going on. I recommend trying to code this out yourself from scratch without even copying and pasting my solution. So try to do this. There'll be the link to this LeetCode page right here by yourself, and that will be it. So if you like this video, please like and subscribe to the YouTube channel. Leave a comment if this really helps you out, because I'll know to do more problems like this. And good luck in your interviews, your real interviews, not LeetCode, problems. So I'm srcmake. Thanks for watching.